Welcome to this session on the instruction set architecture for a processor, where we have in the previous sessions already discussed about what is the typical format for any given instruction in the processor. For example, we had discussed about the fact that one of the fields of the instruction would be the opcode. Following the opcode field, you will also have to code in the instruction what are the places from where the operands are to be picked up, which are to be worked upon. So for example, if you have to do an addition, then which are the two values on which you want to perform the addition, where from those two values are to be picked up from. So the source of the operands is also to be indicated in the instruction. Then you have to also indicate the fact that once the operands have been operated upon and you have the result with you, where exactly is this result going to be stored. So whether it is going to be stored in the memory or whether it is going to be stored in another register, that also has to be part of the instruction. So the source operands as well as the destination operands in any particular instruction could come from different places. For example, the source could be the register, or the source could be a memory location, or the source could be an immediate value which is coded in the instruction itself. Similarly, the destination could be a register, or the destination could be a memory location. So depending upon where from the source is to be picked up and where is the destination, we say that there would be a particular addressing mode in which instruction would be working. What is the need of these addressing modes, and what are these addressing modes typically going to be like? That is what would be the first thing that we will see today. So I will once again be working with 8086 as the example, and taking 8086 we will understand that what are the different possible addressing modes, why do we require them, and how are these addressing modes going to be actually coded in the instruction binary format. Because remember that for every instruction, when it is going to be executed by the processor only understands the machine language, which is a binary ones and zeros. So the instruction has to be finally coded in a string of ones and zeros. So how is this coding done for different addressing modes and for instructions doing different things? We will see some idea of that. So we start off with the different addressing modes and then see the coding in today's session. So the addressing modes with the 8086 as the background processor, as I said that we will check out the salient points about that. So I was telling that for every instruction, the important things to remember would be that from where do you get the operands for this instruction. So these could be the source operands, and similarly where is the result put finally, that has to be indicated in the instruction. So depending upon how are the operands obtained, you will get different addressing modes for the same instruction. So for example, if you take the move instruction of 8086, which moves data from one location to another location, depending upon how the operands are specified, you will get different addressing modes for the same move instruction. So it is essentially going to tell us where the operands are available and how do we get them. So while checking out what are all the different addressing modes which are available, we will also see the answer to the question that why we need these various addressing modes, and what are the various ways of representing the operands. So this particular question, the answer to this would be with us by the end of this discussion. So let's see some of the operating mode, addressing modes which are available in the 8086 processor. So if we check out the addressing modes of 8086, the first addressing mode which is available, the simplest of the addressing modes which is available in the 8086 processor is the register addressing mode. So in the register addressing mode, the operands are in the register of 8086. So if you would recall, there are different registers inside 8086. They can be used as 16-bit registers like the AX and the BX. They are 16-bit registers, or you could use them as 8-bit registers like AL and BL. So if your operands on which you are operating are in the registers itself, then we say that the addressing mode is register addressing mode. So for example, move AL comma BL is an instruction which moves the content of BL register to another register, which is the AL register. So the movement is from BL to AL. Similarly, the instruction add AX comma BX will add two 16-bit quantities which are already in registers, the two registers being AX and BX, and the result will go back into another register which is AX itself. So all operations are happening on values which are already in registers, and we say that this addressing mode is the register addressing mode. So typically, if we will see the composition of the instruction for register addressing, you will see that there would be a opcode which will define what is the work to be done. So for example, whether a move is to be done or an addition is to be done, that is defined by the opcode. And then you will have to code in the instruction the registers on which the move is to be done or on which the addition is to be done. So the rest of the instruction will have codes for registers. So for example, if you are having the move AL comma BL instruction, then in the move AL comma BL instruction, this instruction, two registers have to be coded. The two registers which you will code for would be the AL register and the BL register. So you will take the codes for AL and BL register, go to the register file, from the register file pick out the operands, and once you have picked up the operands, operate upon them. So this is the register addressing mode where the operands are in the register file. The next addressing mode which we have is what we call as the immediate addressing mode. So in the immediate addressing mode, the main idea is that the operand is part of the instruction. This is the key idea behind the immediate addressing mode. The operand is part of the instruction itself. There is no memory reference required to fetch the operand. So operand is fetched along with the instruction. You don't have to do a separate memory reference to fetch the operand. When you will fetch the instruction, along with the instruction, the operand would be fetched. So for example, if you take the first instruction here, which is move AX comma 23 hex, the code for this instruction would have fields where, if I see typically what will be the complete code for this instruction be looking like, move instruction, well, I will see that I will have opcode which will tell me that okay, I have a move operation to do. The second thing which I will code for in this instruction would be the code for the AX. So there is a register to which a move is required to be done. So the code for AX has to be part of the instruction. And the third thing which I will code in the instruction itself would be this immediate value 23 hex. So 23 hex will take another 8 bits to code, and when I will fetch the instruction move AX comma 23 hex, I will fetch this complete bit sequence. So already the value 23 hex would be there with me. All that I will do when I will execute this instruction would be that this value which I already have with me, that is 23 hex, I will sign extend it and put it in the AX register. Remember that 23 hex is 8-bit, AX is a 16-bit register, so you need to do a sign extension and put the value in the AX register. Similarly, add CL comma 44 hex. So the value 44 hex is part of the instruction itself. Similarly, if you say move AL comma within quotes A, so this means that whatever is the ASCII representation of the character capital A, the 8 bits corresponding to that would be moved to the AL register. And in general, you could move any immediate value to the register. So you can see here that as far as this immediate addressing mode is concerned, one of the operand, which is the destination operand, is a register, and the other is an immediate value. But this immediate value is coded along with the instruction, and I don't do a separate memory reference for getting these values and then putting them in the corresponding registers, or for that matter any memory location. So the main idea behind providing such a addressing mode is that many a times I would have situations where I would be working with small integer or small constant values. So this situation would be very common. So if these small constant values, integer values, were to be fetched from memory location, it would slow down the execution of the instruction, because every time I go and access a memory location, I spend a lot of time. On the other hand, if I could get the values on which I have to operate upon from inside the processor itself, then the operation can be faster. So as this would be a common case, that is, I would be working on a small constant very frequently. So these small constants I can code along with the instruction, and once I have coded them along with the instruction, I will fetch them along with the instruction, and hence the execution of the instruction would not require any separate memory reference, and hence it would be faster. So this is the second addressing mode, which is the immediate addressing mode. The first was the register addressing, which we have already seen, and this is the second addressing mode. The third addressing mode that you will find in, for example, 8086 processor is what we call as the direct addressing mode. And this direct addressing mode is one of the modes where I can get one of the operands from a memory location. So the typical composition of this addressing mode would be, for example, as you can see here, you have something like move CX comma data or move CL comma temp, where this data and temp are actually memory locations. So these are memory locations. Or if you are very explicit, you could say move AL comma within square brackets. So these square brackets are important. Within the square brackets, a memory location. So this is how we write the direct addressing. So if you are to code such an instruction, as you can see, the first thing that you will require is once again the opcode. So whether you want to do a move or whether you want to do an addition, that you should tell using the opcode. The second thing that you will require is that you will be required to code for a register. So for example, CX you might have to code, or CL or AL, the code of the register would be important. And the third thing, of course, that you will require is you will have to code for the memory location. So the 16 bits that are to point to a offset in the memory is to be coded. The way in which this instruction would work, for example, if you take the last instruction, which is this move AL, 1, 2, 3, 4, if you take this last instruction, it is essentially saying that I will go to the data segment, and in the data segment I will go to a offset of 1, 2, 3, 4 hex. From that offset I will pick up a byte. So from this memory location I will pick up a byte, and I will move that byte into the AL register. So this is how the direct addressing would typically work. You could have moved a value from a register to a memory location as well. So that is also perfectly feasible and can be done. So for example, I can write the instruction move within square brackets 1, 2, 3, 4 hex, comma, AL. So the way in which this instruction would be working is that the value in the AL register, the byte size value in the AL register, will be moved to a memory location which is in the data segment at an offset of 1, 2, 3, 4. So this is an example of direct addressing. Typically, direct addressing would be used when you want to do a single move. Say for example, you just wanted to move a byte size value from a register to a memory location, or you wanted to move a value from a memory location to a register, and it is just a single move that you want to do. So in that case, you could just simply use the direct addressing mode. So this is the third addressing mode which is available in 8086. Moving ahead, the fourth addressing mode in 8086 is what we call as the register indirect addressing. Register indirect addressing. So register indirect addressing is essentially saying that the offset, one of the operands, is at an offset which is indicated by the contents of a register added to the DS register value. So for example, I could write an instruction, as you can see here, I could write an instruction which will say move AX, comma, within square brackets, let's say I will use BX. So the way in which this instruction would work would be that I will go to a memory location in the data segment at an offset equal to the contents of BX. So BX, remember, is a 16-bit register. So I have a 16-bit offset in BX. So the contents of BX are indicating an offset. So the offset is indirectly obtained from the contents of BX. So take the contents of BX, add them to the contents of the DS register which is left shifted, and that is going to give you the memory location. So from that memory location, read a word. In case, for example, here if the register is AX, that means you are working on word sized values. If it was AL, you would have been working on the byte sized values. So the typical translation would be that the things that I will code for in the instruction would be the opcode, which will tell me whether a move or a addition is what I am doing. Then I will be coding for example, for the AX register. So that's the destination, for example, with which I am working. and then I need to code for the register from where I have to pick up the offset. So the code for BX, for example. So that is typically minimum which will be required in the instruction. So you pick up the code for BX, read the contents of BX here. The contents of BX will point to a offset in the data segment for you. From there, pick up a value and move it to a register. So the offset address is indirectly specified inside a register. That's why we say it is a register indirect addressing. Now the main advantage of this addressing comes from the fact that supposing that I wanted to move an array of bytes from starting from some memory location and ending at some other memory location to some other place. So what I will have to do is essentially I will have to go on reading a byte followed by another byte and so on. So a sequence of bytes from a memory location I will have to read. So what I could do is I could initialize my BX register to the starting location of the array, and then I say move AX within square brackets BX, and then what I could do is simply I could increment BX by 1 after I have got the value from this memory location. Shift the value from AX to wherever you want it to be shifted, and after you have done this shifting you will have to increment BX by 1. So you can do a incrementation by saying add BX comma 1, and then you can go back and do the next move. So all that you have to do is you have to continuously go on increasing BX value by 1, and you can go to the next location in the memory, get the new values from that location and do a shifting. So this is the importance of the register indirect addressing. The example of register indirect addressing, one more example of register indirect addressing is given here, where we say that okay, you assume some values for the DS register, assume a value for the SI register and the AX register. So the question is that what will be the contents of the memory location modified after the execution of the following instruction. So the instruction is this. So the contents of AX register are to be moved to a memory location which is pointed to by SI. So remember that the memory location, the effective address, how you will calculate would be that SI is pointing to a offset in the data segment. The data segment is starting at a location 11200, left shift and get a 20-bit address, left shift by 4 bits, get a 20-bit address. So from a 16-bit value get a 20-bit value. So that is the starting location of the data segment. To that starting location of the data segment add the offset, which are nothing but the contents of SI. So SI is right now 2145, so add that to the DS value, and this is the memory location at which the contents of AX will be moved. The thing to remember here is that AX is a 16-bit register. So actually you are moving to 2 memory locations. It's not just a single memory location. You will move to 2 memory locations, 13345 and 13346. So the significant part of 1234 will go to 13345 and 34 will go to 13346. So that is the movement that will happen. It will be done to 2 memory locations. Had this been, let's say, had this instruction been move within square brackets si, comma al, then it would have been a single byte which would have been moved, and the movement would have been to only 13345. That's the only movement that would have been there. So this is how the register indirect addressing works. There are certain small important points which should be kept in mind while you are using register indirect addressing. So for example, if you take the first instruction shown here, which is move al comma di, I know that this instruction means that from a memory location in the data segment at a offset pointed to by di, read a byte and move it to al. So this register here, al, is a register which is a 8-bit register. So I know very clearly that the move is a byte-sized move. So I can code it without any ambiguity. But if you take the next instruction which is shown here, you will see that you have a problem. So if you just say move within square brackets BP, comma 10 hex. So BP is pointing to a memory location, starting of a memory location, and you have a value 10 hex to be moved. So you really do not know whether you are talking about a byte to be moved or whether you are talking about 0010 hex to be moved. So whether you are talking about a word size value to be moved. So if you just write the instruction as shown here, the problem would be that the assembler would find it ambiguous and it will raise an error condition. The assembler would not know whether it is 0010 which is to be moved or it is just a byte size 10 hex which is to be moved. So to make it explicit for the assembler and to remove the ambiguity, sometime what we do is that we could put a assembler directive which is byte PTR. So this assembler directive is essentially telling the assembler that a byte size value 10 hex is to be moved to a memory location being pointed to by DI in the data segment. Suppose that you wanted to move a word size value, you could use the assembler directive word PTR. So instead of byte PTR, you can use the word PTR assembler directive. So these directives are used only with instructions that use memory locations through a pointer or an index register with the immediate data. So these directives will be required in those situations. So these are the finer points about using the register indirect addressing mode. The next mode which is available in 8086, the next addressing mode which is available in 8086 is the base plus index addressing mode. It is similar to the register indirect addressing mode except for the fact that in this instruction the offset is calculated as a sum of two registers. In the register indirect addressing mode, the one which we were just talking about previously, the offset is contained in only a single register, while here it is calculated as a summation of contents of two registers. So typically we will use one of the registers would be BX or BP. So use one of the registers as BX or BP, which will hold the beginning location of array, for example, and the other register would be DI or SI. So those are the possible combinations that you can use. So as in this example, you can see that these are typically addressing modes which can be used to address different arrays. So if you are accessing elements from one array at a given point of time, one after the other, and at certain other point of time you want to shift to certain other array and start accessing elements from that array. All that you have to do is that the base of that array, you could put it in the BX or BP register, and then the offset within the array could be contained in the DI or the SI registers. And you could use a format which is, for example, shown here, move to AL, BX plus SI. So essentially in the DS segment at a offset BX plus SI, from here I want to read a byte and put it in the AL register. Supposing that instead of the AL register I was using a AX register. So let us say that I was saying move to AX BX plus SI. So suppose this was the instruction. So in this case I would be reading two memory locations. I will be reading this memory location and the next memory location. So 2 bytes I will read, and after reading the 2 bytes I will shift the contents to the AX register. So it will be a word size move. So this is the base plus index addressing mode of 8086. The next addressing mode is what is known as the register or base relative addressing. So as you will see that this is similar to the base plus index addressing mode which we were just talking about, except for that one of the elements which are used for calculating the effective address is a immediate value. So you will be accessing data in a segment of memory which is obtained by adding the contents of a base or an index register. So you could have BP, BX, DI or SI, and a displacement. So the typical example is given here, for example. So you have a BX register and you have offset, immediate value of the offset is specified. So the memory location which will be accessed would be that to the DS, inside the DS data segment, I will go to a offset which is given by BX plus the displacement. So from this offset I will pick up the value and move it to the AL register. So this addressing mode can also be used to pick up a particular value from an array. So for example, you know that your array starts from this particular location and you want to pick up the element number X. So all that you have to do is that the starting location of the array, you should put it in any of these BX, BP, DI or SI registers, and the element value, element number value, that you can put it in the immediate part of the instruction. And using this addressing mode directly you can access the value. So this is the base relative addressing mode of 8086. Now the last addressing mode that is available in 8086 is what we call as the base relative plus index addressing mode. So base relative plus index addressing mode is essentially used for addressing 2D array of data. That's where you can use it. The previous addressing modes which we were discussing, they were mostly used for addressing arrays. So you could address a particular element in an array, or you could address consecutive elements in the array. So it was a single dimensional array that we were talking about. Suppose that the data structure with which you are dealing is a 2-dimensional array. So if it is a 2-dimensional array, then how do you access elements from within this two-dimensional array. So the way for you would be that use the base relative plus index addressing. So as this example here shows, the effective address would be calculated as summation of contents of two registers and immediate value which is added to the contents of these two registers to produce the effective final displacement in the data segment. So the instruction which is given in this example, the way in which it would work would be that in the data segment you will go to a offset given by addition of contents of Bx to the contents of Si to the displacement, the immediate displacement which is specified here. So from here read the values and put it in the AL register. Effectively you can access an element of a 2D array by changing or manipulating the values in the Bx and the Si registers. So this is the base relative plus index addressing mode. So these are the different addressing modes available in the 8086 processor. You can see that there are quite a many addressing modes available, and through our discussion you would also appreciate the fact that there are different situations in which you would want to use a particular addressing mode to your advantage. Not only are these addressing modes going to be useful in case you are only working with registers, or in case you are working with immediate quantities, or in case you are working with memory. Even within memory, you have different ways of accessing a particular memory location. And the main idea behind why these different ways are provided is the fact that the element that you are picking up from the memory could be just something as simple as a single element, or it could be an array, or it could be multi-dimensional array. So depending upon what is the problem at hand, you could pick up a particular addressing mode and use it to your advantage. More are the number of addressing modes that are available to you, more would be the flexibility that you will have in writing a program for solving a particular problem. But then more are the addressing modes which are available to you, more would be the complexity of the underlying hardware which would be required to execute these instructions which are now coming in different formats. We can just check out one example based upon the different addressing modes that we have seen, particularly the last addressing mode that we were talking about. So in this example you can see that we have written a simple code where we want to access different elements within a file. So in a file I might have records, and in the records I might have different fields. So at any point of time inside a file I may want to access a particular record and a particular field of that record. So we have just written a small code to help you appreciate this particular fact. So you have a file and you have two records. So when you say you have a record A dB, so the size of every element of the record is byte, and you have 15 bytes reserved for record, and these bytes are uninitialized. Similarly, you have another record starting at memory location immediately after the first record ends, and you have 20 bytes in that, all are uninitialized. So when this program is actually going to be loaded in the memory for execution, you can imagine that the RECA, record A, would start in the data segment. So somewhere in the memory, when this program will be executing, there would be a space allocated to this program which will define the data segment for this program. So starting at a offset of all zeros in the data segment, next 15 bytes would be record A. Then starting from the next location, that's here, I will start storing values for record B, and that will go to another 20 locations. So at a offset 0 in the data segment, you can imagine that your record A will start, and then after 15 bytes record B will start. So if I was to access any particular memory location from the data segment, I could say that I would move into the BX register the offset at which the record A starts. Remember that the record A will start at an offset of 0. This is where A is starting. So in BX, I would have a all 0 value. And say I initialize DI to all 0. And then I say move BX plus DI. So the first element is what I am trying to access. And file, you can see from this directive, it says that file is also pointing to the memory location, which is the starting memory location for record A. So it would be essentially 0 plus 0 plus 0. So the first element is what I will be accessing. I could have incremented the values of BX, and I could have incremented the value of DI, and I could have gone to the other memory locations for accessing the data from those memory locations. So that is something which I can make use of in case I wanted to access multiple data from different memory locations. So this was just an example for us to understand the way in which I could be accessing different memory locations. So this was a small discussion on what are the different addressing modes that you could have available to you with 8086 processor as an example, and this is typically what you will have in available to you in the present day processors. Now the next thing would be, so for example, as I was telling you, the present day processors, for example, if you see the Pentium addressing modes, you will see there are 12 addressing modes which are available. So typically in Pentium you would have a starting address plus an offset which will give you a linear address, and in case you have paging enabled, you will translate it from the virtual to the physical address and get the data. So paging is a concept which you will learn in the operating systems, where essentially we will be generating virtual addresses from the processor, and I would have a page table which will translate it and give me the physical address from where the actual entity is to be picked up. This is typically done for managing multiple processes which might be running in your machine. So you will learn more about this in the operating systems course. The 12 addressing modes which are available in in Pentium processor, for example, are defined here. Some of them we have already seen in the 8086 processor, for example, immediate, register, displacement, base plus displacement. All these we have seen. There are a few more available, for example, scaled index, etc. So these are few extra modes which are available in the Pentium processor. Now, once we have seen the addressing modes, different addressing modes, practical addressing modes which might be available to me, the decisions which I will have to take based upon how many, for example, how many addressing modes I will be able to support, how many instructions, varieties of instructions I should have. All these will have an impact on my instruction set architecture. So as I was telling, for example, what all instructions do I want to support? So do I want to support, for example, instruction like swap, which can swap the contents of two registers, or do I don't want to support that? So I can still do swapping by doing a movement from one register to another register, but do I still provide for an explicit instruction like a swap or not? So that decision will have an impact on the final architecture that I will end up with. So how many operations do I want? What should these operations be able to do? And how complex can they be? So for example, I could have an instruction as complex as saying that it could be adding contents of two registers, then the result it could be multiplying with the contents of the third register, and the final result it could be putting in another register. So complexity of the instruction can be high, but then when you are executing these instructions, it may take a long time. And secondly, you have to code for these instructions, and this coding could itself be complex. So you will have to finally decide upon how many operations, what can they do, and what is the complexity that you are willing to take up. What are the different instruction formats that you will use? That is another question to be answered. So what is the length of the opcode field? This will be decided by the fact that how many unique instructions do you have, how many addresses you will have. So all this would tell you what are the instruction formats with which you would be working. How many registers do you want? That's another design decision that you will have to take. So do you want to work with only a few registers, or do you want to work with a large number of registers? A large number of registers will make the life of the programmer easier. I would have a number of registers available for me to manipulate values. But larger is the number of registers, more is the space which my register file will take on the CPU. So more is going to be the cost. Now, which is the optimum value of registers with which I should work? That is a design decision that I should be in a position to take. Similarly, of the different addressing modes which are available to me, how many modes do I want to support? The different addressing modes which we were talking about just now, we saw that in 8086 there are quite a many addressing modes. Similarly, in Pentium processor we saw there are 12 addressing modes. So more are the number of addressing modes available, lesser would be the complexity of the programming, but more complex is going to be the underlying architecture on which these instructions will execute. So these processors like 8086 and Pentium processors typically fall under the category of CISC processors, complex instruction set computing processors, where you will find a large number of instructions of all varieties and which have a large number of addressing modes also. On the other hand, there is another class of processors which is known as the RISC processors, reduced instruction set computing. These processors you will find will have a few simple instructions. They will have only a few addressing modes. So few instructions with few addressing modes make the underlying architecture on which these instructions execute very simple. And simplicity means fastness. So these processors can be very fast. And of course, they will have a drawback. And the drawback would be that since I have very few simple instructions and a very few number of addressing modes, the code for doing a particular work would be larger in case of RISC processors, and the code for doing the same work in CISC processor would be smaller. But that necessarily does not translate into the amount of time which is taken. Larger code could take a smaller amount of time, and a smaller code could take a larger amount of time. So that's a different discussion altogether. So these are the different design decisions with which we will have to work. This slide is telling you about the same idea which I was discussing. So more addresses, more addressing modes if you have, more addresses if you have, you will have more complex instruction. You will require more registers to be able to do the work. Of course, inter-register operation is quicker, so you may be able to quickly execute the instruction, and effectively it will translate to fewer instructions in your program. Similarly, if you were operating, when I'm saying here how many addresses in an instruction, we are talking about how many operands can we support in an instruction. So if you have fewer addresses or fewer operands in your instruction, your instructions will be less complex, but they may not be very powerful instructions. They may be able to do only simple things. Similarly, you will require more instructions per program to do the same thing. If you have fewer addresses, then you will require a larger number of instructions to be able to do the work. And of course, this would mean that since the instructions are simple, there will be a faster fetch and execution of these instructions. Let's take up an example and check out that how do different number of operands in a given instruction could impact the way in which we write the program to solve a particular problem. So the problem with which we will work is a simple problem. Let's say that I wanted to do this operation. So Y is a register for me inside the processor, and I want to do a calculation where I have 5 values A, B, C, D, E. I want to do a minus B divided by C plus D multiplied by E. So how would I write a program to do this if I have, let us say, a 3-address machine? How would I do it if I have a 2-address machine? And similarly, how would I do it if I had a 1-address machine? So let's see them one by one. So supposing that you have a 3-address machine. So 3-address machine would mean that I can support instructions like add A, B, C. So that would mean that contents of B and C can be added and they can be put in another register A. So up to 3 operands I can specify. That's what I mean by saying that I have a 3-address machine. So this is how we will solve the problem if we have a 3-address machine. So we say that the first instruction would be I will do a subtraction of A and B and put the result in the register Y. After that, I will do a multiplication of D and E values and put the result in another register T. So T is my temporary register available to me in the processor. After I have done D into E, I do a addition of T and C. So T already has a D into E, so to that I add a C and put the result back in T. So I have done this part. And then finally I do a divide. So I divide Y and T, put the result back in Y. So in a 3-address machine, you can see that I require only 4 instructions to be able to do this work. Very small and compact code, but you can see that the instructions by themselves are pretty complex. They have 3 addresses associated with them. Supposing that the same work I wanted to do on a 2-address machine. So if you want to do this on a 2-address machine, what would the code be looking like? So you have now only 2 addresses. So you will have instructions like add A, B. So that would mean that the contents of A and B can be added and the result will go back in A. So one of the registers is a default implicit location where the result will go back to. So this is how a 2-address machine would work. So first of all, what we need to do is, since we have only 2 addresses available, move the value A into the register Y. So that's the first instruction. Then subtract B from that. So A minus B those contents are available to you in the register Y now. The next thing that you do is move D value to the temporary register T. After you have moved it to the temporary register T, multiply it with E. Then add C to that. So at the end of this add instruction, C plus D into E, that is available to you in the register T. And then finally do a divide. So you can see here that the number of instructions that we end up using for a 2-address machine are 1, 2, 3, 4, 5, 6. For a 3-address machine, we finished the work in 4 instructions. I require, in this case, 6 instructions. Now suppose that the same work, if you just extend the example, if we wanted to do the same thing with a 1-address machine, how would we do that? So 1-address machine means that one of the operands is implicitly going to be in the accumulator. So move the operand to the accumulator and then operate upon that. So if you had a 1-address machine, this is how it would look like. So first of all, put in the accumulator, load in the accumulator the value D. Once you have loaded the value, multiply it with E. So that would mean that you are multiplying D with E and the result is back in accumulator. So to that value in the accumulator, add C. Now the accumulator contains this part, C plus D into E. Store this value into your register Y. So now Y has this value. After you have done that, you have to do A minus B as well. So load into the accumulator A and subtract B from that. So after this, what you have is that in the accumulator you have A minus B. So now that value which is in the accumulator, that you want to divide by Y. So that is what you do by saying div Y. The result at the end of this operation is in accumulator. So the result has to be finally taken to the register Y. So use this instruction to move the result to the register Y. So at the end of this operation, the register Y will contain the value as required. So you can immediately see here that the number of instructions that we require for 1-address machine to be able to do the same thing is more. So in general, you will see that if the number of addresses available to you are more, you will be able to do the work in a smaller number of instructions. Lesser is the address operands available for me to work with, more is the number of instructions that I will take. But then, as I had said, that you should be careful of the fact that it also does not necessarily mean that 3-address machine would be faster. Although the number of instructions are less, the amount of time which it may end up taking could be more. So only thing that we can conclude would be that if the number of addresses available to you are less, then more effort in programming, writing the program is what you will have to put in. So in this discussion today, we have seen the different addressing modes. We have seen that what is the impact of different amount of addresses available in the instruction. The next thing that we need to check out and which we will do in the next session would be that how are these instructions actually coded. So we will once again work with the example of 8086 processor and check out that how can we code at least one of the instructions we will take as an example and see that what is that is involved in the complexity of the coding in case I have multiple addressing formats and addressing modes available with me. Today we will stop at this point. Thank you.